Okay, so in this example, we're going to look at a slightly different parametric curve. Our parametric curve is going to be x equals cosine 3t, y equals sine 3t, and we're going to be on the interval from t equals 0 to t equals 2 pi. Okay. The plot of this is exactly the same as our last example. Oh my. Okay. So this is still a circle of radius 1 centered at the origin. Okay, oriented counterclockwise. Okay, so let's follow the exact same procedure we did before, and let's investigate what's going on. So the integral alpha to beta of dx dt squared plus dy dt squared dt. Okay, let's compute dx dt. dx dt should be negative 3 sine 3t, and dy dt should be equal to 3 cosine 3t. Integral from 0 to 2 pi, square root, this becomes, we can do the square, so this should be 9 sine squared 3t plus 9 cosine squared 3t dt. Integral 0 to 2 pi, 2 pi. I can pull out the 9 from everything. Again, sine squared t is 3t plus cosine squared 3t is 1. So this is going to be equal to the integral from 0 2 pi of square root of 9 dt. Square root of 9 is also 3. So this is 3 integral 0 to 2 pi dt, which is 3t evaluated at 0 and 2 pi. So this should be 6 pi minus 0, which is 6 pi. Okay, so what happened between this one and the last one? So in the last one, we integrated from 0 to 2 pi of cosine t and y equals sine t. And so we saw that we went around the circle once. What's going on here is notice the argument of cosine and sine has changed. So what this means is we're not going around the circle only one time, we're really going around the circle 3 times. So the curve looks exactly the same, but we're going around the circle once, twice, and 3 times. So how do we end up with 6 pi? We go around the circle 3 times, and we end up with 3 times 2 pi, which is 6 pi. Okay, so be careful when finding your endpoints. If you just want to find how long the arc is, the arc, in this case, would only be 2 pi, but we're thinking about this in terms of a model of how particles travel. So what's really going on with the particle is traveling 6 pi. Okay, so one other note about this, if we can do something like this for arc length, it means we can also do something like this for surface areas of revolution. Okay, so our surface area of revolution is going to behave exactly more or less as you would expect. Okay, so this would be about the x-axis would be this. So your surface area of revolution should be the integral from alpha to beta of 2 pi times your radius. Your radius in this case is going to be y of t times your arc length. We just found the arc length. Okay, and if you're about the y-axis, the only thing that changes is this. This would become x of t. Okay, so let's do this with a quick example. Okay, so let's find the surface area of a sphere of radius r. Okay, so a sphere of radius r, we can get in the following way. So let's take the following parametric curve. We're going to let x of t be equal to cosine t, y of t be equal to sine t, and we're going to let t go between 0 and pi. Okay, so, and we're going to rotate it about the x-axis. This way we get the top semicircle, and we take that top semicircle, rotate it about the x-axis, we're going to wind up with the full sphere. Okay, and recall surface area of a sphere should be equal to 4 pi r squared. Okay, and that parametric form isn't quite right. I want a sphere of radius r, so this should be a circle of radius r, so I can do that by just multiplying by r. Okay, so that means my dx dt should be negative r sine t. My dy dt should be r cosine t. So my surface area integral is going to become integral from 0 to pi of 2 pi times r, which we said, our radius, which we said should be y, is r sine t, times the arc length, which I can factor out an r squared from everything first. Let me write it like this. So r squared sine squared t plus r squared cosine squared t dt. We can factor out an r squared. We're left with sine squared plus cosine squared t, which is 1. Square root of r squared is just r. So this becomes, we can pull out a 2 pi r squared times the integral from 0 to pi of sine t dt. Okay, basic antiderivative, we can use the fundamental theorem of calculus. So this is 2 pi r squared. Take the antiderivative, this should be cosine t evaluated at 0 and pi, negative cosine t. So it should be 2 pi r squared times minus cosine pi plus cosine of 0. Cosine of pi is negative 1, so minus negative becomes 1, plus cosine of 0, which is also 1. So that's 2. 2 times 4 pi, times 2 pi r squared is 4 pi r squared, exactly like we said it should be. Okay, so hopefully after this you have an appreciation for the fact that we can use calculus on parametric curves, and we can even do some of the more interesting examples and applications that we could do before, but now with uh, more fun curves. Okay, so thank you. Enjoy your day.